I'm a seismologist here at GNS Science in New Zealand, which is a place where we have lots of earthquakes. We can have big earthquakes most places in the country. And one particular aspect I look at is aftershock hazard and how we can calculate probabilities of that and what that might mean. When we get a large earthquake, we get lots of smaller earthquakes that occur after those, and those are what we usually define as aftershocks. In New Zealand, we can have earthquakes anywhere, and this is a map of the country where basically the hotter the colors are mean that the higher the probability there is for some sort of ground shaking of the subduction zone in this area. Then we move to the long strike slip fault, the alpine fault through here, where we have the highest hazard in the country, and then again some subduction down in this area. But what you can see is that pretty much anywhere in the country we have probabilities of ground shaking. We can have earthquakes anywhere. We have the lowest areas up in Northland, and down south we have lower seismic hazard. And then we have Christchurch, where we've had all the recent activity going on. Is certainly not the highest area in the country, but is an area that we do expect to have earthquakes occurring. So once one of those larger events occur, then we have some increased probability that of earthquakes due to the aftershock sequence. So the aftershock model that we give the forecast from, was developed based on what we know about the behavior of aftershock sequences around the globe using what we've learned in the last 100 or 150 years. And then we tune that model to the particular behavior of New Zealand aftershocks. So now if we move on to the aftershock sequence that has occurred since September in the Canterbury region, each one of the yellow dots represents the number of aftershocks greater than magnitude 4 that occurred in each day that's represented on the time scale down on the bottom here. So if we look at this dot, that shows that roughly probably 19 earthquakes greater than magnitude 4 occurred on that particular day. And then if we get down to what you see as a line down here, that's essentially saying that on these days there were no aftershocks greater than magnitude 4. And then the black line that kind of runs right through the middle of everything, that represents the forecast that we were able to calculate prior to these events occurring. So that's the information that we give out, saying this is roughly how many you can expect on any given day or over a longer time period. But this is only an average that we're showing, so it does change. So you have certain days where you get more than maybe you would have initially thought, and then other days you get none, you get the 0. So it's a long-term average that we're looking at. So if we look specifically at this time period in here, which is prior to the occurrence of the event, the magnitude 6.3 in February, there was an expected rate of earthquakes greater than magnitude 4 that was quite low. It was less than 1 magnitude 4 per day. But then when we start looking at in more detail, we can see that if that does allow for the probability of a larger event to occur. The core of the way we are able to model the aftershock sequences is that every aftershock that occurs has some probability of its own little aftershock sequence occurring after it. And that's what we've seen both in February and then in June, is that these larger aftershocks really had a significant impact on the behavior of the overall aftershock sequence. So this is an example of what I'm talking about here. Along came this magnitude 6.3 in February, and it brought to life its own little aftershock sequence based on the 6.3 that basically just got superimposed or layered on top of the aftershock sequence that was already occurring from the magnitude 7.1 that occurred in last September. So then those two sequences kind of combined together, whereas the aftershock sequence from the magnitude 6.3 is really a much smaller sequence than from the magnitude 7.1. So the aftershocks from that essentially decay away much more quickly, and then what we get back to is that we eventually get back to the level of aftershocks that we were having from the magnitude 7.1. So using what we understand about the behavior of aftershocks and aftershock sequences, we can develop mathematical models that we can then use to provide forecasts of what sort of aftershock activity we expect in the coming time periods. This is a 24-hour aftershock forecast map. So this is showing the forecast from 11 a.m. today till 11 a.m. tomorrow, and it's just showing probabilities of some sort of strong ground shaking. So the probability that you really feel an earthquake in this time period. So you can see that the highest probabilities are really focused on this aftershock region, the entire aftershock region for for these Canterbury events, but then you can also see that there's little bits of activity that are going on in other areas of the South Island, but at much smaller probabilities, and these are just to some other small earthquakes that have occurred in the region. We're not able to predict earthquakes, so we can't ever say exactly when any earthquake is going to occur, but we can understand the range of possibilities. So based on that information, we can give a probability of what we expect to occur. Now that doesn't mean that something will occur for sure, but it just allows for the possibility that may happen. That's the information we have.